At the 2 nanometer node, silicon atoms are spaced 0.5 nanometers apart. The gate dielectric is only a few atomic layers thick. Quantum tunneling becomes the dominant failure mode as electrons spontaneously bypass the potential barrier. Traditional planar transistors rely on a flat channel surface. As dimensions shrink, the gate loses electrostatic control over the charge carriers deep within the substrate. This creates a leakage path that wastes power even in the off state. The industry transitioned to thin field effect transistors to regain control. By pulling the channel up into a vertical fin, the gate wraps around 3 sides. This increased surface area improves the drive current and reduces leakage. Below 5 nanometers, FinFETs face physical limits. Increasing the fin height to improve performance makes the structure mechanically unstable. Furthermore, the gate cannot control the bottom of the fin effectively, leading to short channel effects. Gate-all-around field effect transistors solve this by fully surrounding the channel. The channel is divided into multiple horizontal nanosheets, stacked vertically. This geometry ensures the gate electric field penetrates the entire conducting volume. Fabrication begins with epitaxial growth of a superlattice. Alternating layers of silicon and silicon germanium are deposited on a wafer. The thickness of these layers determine the final nanosheet height and the spacing between them. A highly selective chemical etch removes the silicon germanium layers while leaving the silicon nanosheets intact. This process creates horizontal suspended bridges. The resulting voids are where the gate stack will eventually reside. Inner spacers are deposited at the ends of the channels. These dielectric layers reduce the parasitic capacitance between the gate and the source or drain. Precise control of spacer width is critical for switching speed. The gate stack is built using atomic layer deposition. This technique deposits a high K dielectric and work function metals one atomic layer at a time. This ensures uniform coverage, even in the narrow gaps between nanosheets. The threshold voltage is tuned by varying the work function of the metal gate. By using different metal alloys, engineers can create transistors with multiple power and performance profiles on the same chip. The primary advantage of gate-all-around is electrostatic integrity. Because the gate surrounds the channel, it suppresses drain-induced barrier lowering. This allows for shorter gate lengths without increasing the off-state leakage current. Gate-all-around transistors achieve a subthreshold swing closer to the theoretical limit of 60 millivolts per decade. This means the transistor turns on and off more sharply, allowing for a lower supply voltage and reduced power. Unlike FinFETs, which are quantized by the number of fins, nanosheet widths are variable. Engineers can widen the sheets for high performance or narrow them for low power. This flexibility optimizes the power-performance area metric. By stacking multiple nanosheets, the effective channel width per unit of footprint is maximized. This high current density enables faster switching of parasitic capacitances in the interconnect layers, boosting overall processor clock frequency. Thermal management is a significant challenge for nanosheets. Surrounded by low thermal conductivity dielectrics, the silicon channels struggle to dissipate heat. This self-heating effect can degrade carrier mobility and long-term reliability. To support 2 nanometer transistors, the industry is moving power delivery to the backside of the wafer. This separates the power network from the signal interconnects, reducing voltage drop and freeing up space for signal routing. Buried power rails and nano-through-silicon vias connect the backside power network to the transistor source and drain. This reduces the resistance in the power delivery path, allowing for more stable operation at high frequencies. As transistors shrink, contact resistance becomes a bottleneck. Advanced liners like ruthenium or molybdenum are used to minimize the barrier between the metal and the semiconductor. This ensures that the drive current is not restricted. The 2 nanometer node is only possible through extreme ultraviolet lithography with high numerical aperture. This allows for the patterning of features smaller than the wavelength of the light itself, reducing the need for complex multi-patterning. The Forksheet transistor is a proposed evolution where an insulating wall separates N-type and P-type nanosheets. This allows them to be placed closer together, reducing the cell area and decreasing the parasitic capacitance between gates. The ultimate scaling limit for silicon may be the complementary field effect transistor. Here, the N-type and P-type transistors are stacked directly on top of each other. This vertical integration could double the density of logic circuits. Future gate-all-around devices may replace silicon with high-mobility materials like molybdenum disulfide or other two-dimensional semiconductors. These materials allow for ultra-thin channels that maintain excellent mobility even at 1 nanometer. At 2 nanometers, surface roughness scattering significantly impacts mobility. Any atomic scale irregularity on the nanosheet surface acts as a barrier to electron flow. Atomic layer etching is used to achieve perfectly smooth channel surfaces. Quantum confinement alters the band structure of the semiconductor in thin nanosheets. The effective mass of the charge carriers changes, which can be leveraged to increase the injection velocity and improve the switching speed of the device. Manufacturing gate-all-around transistors requires unprecedented precision. A variation of just 2 or 3 atoms in sheet thickness can cause a significant shift in threshold voltage. Advanced metrology and machine learning control the fabrication loops. While transistor density increases, the wires connecting them struggle to scale. Increasing resistance and capacitance in the metal layers limit the performance gains. New materials like graphene-capped copper are being explored to overcome this bottleneck. Gate pitch scaling is the primary driver of density. By moving to gate-all-around, the contacted poly pitch can be reduced below 40 nanometers. This allows for more transistors per square millimeter than any previous technology node. Gate-all-around provides a lower leakage floor, which is critical for mobile and edge computing. It allows devices to maintain high performance while extending battery life through superior control over the subthreshold region of operation. The transition to gate-all-around increases the number of mask layers and process steps. This complexity drives up the cost per wafer. However, the performance per watt improvement justifies the investment for high-end artificial intelligence applications. 2 nanometer gate-all-around transistors represent the pinnacle of silicon engineering. As we approach the atomic scale, the industry must innovate with new architectures and materials to continue the historical trend of increasing computational power.